Today we're going to take and we're going to talk about a new type of free fall problem. It's one where we take and we go up and then we have something that comes back down. A couple things you do need to remember is that free fall is not to be confused in physics with free falling, like jumping out of an airplane. Their air resistance is very important, but in what we're talking about, remember, we ignore air resistance. So let's say we take and we throw a ball up and it comes back down from height. So our two assumptions here are that there's no air resistance and that we are throwing it and catching it at the same height. Right? So those are two assumptions we will use. Now, if you take a look here, down at the very bottom of this picture, if you notice, we're going to take and we're going to throw the ball up with a velocity of 20 meters per second, and the positive sign tells us that we're taking and we're considering it going up in the positive direction. Over here, it's coming back down, and it's a negative 20 meters per second because it is heading towards the ground. Now, as we take and we go up to the top and we come back down, I want you to notice that this is a very symmetrical path. Okay, this takes and it forms a parabola. If you've done your math with parabola, you know that it is a squared function. So as it takes and it goes up, everywhere on the path going up and coming down, if it's at exactly the same height, you will notice that the velocities are the same. The only difference is the sign. So right here as we take and we throw it up at the bottom, it has a velocity of 20, positive 20, and as it's coming down, it has a velocity of negative 20. Right here, we have a positive 20, and over here at the same place, we have a negative 20. Up here, again, we have a positive 10 meters per second. Here we have a negative 10 meters per second. One thing I do want you to notice is the velocity right here at the very top of the path. The velocity is 0, okay, because we're going from the positive direction to the negative direction. So for a very split second here at time 2 seconds, we take and we actually stop momentarily before we start accelerating back towards the earth. So the velocity does actually go from a positive, it passes through here, and it starts to become negative as it takes and it comes to the bottom. So how do we take and we calculate things like this? Well, what goes up must come down due to gravity. So let's say we have a problem that asks, how long does a baseball catcher have to get into position if a foul ball is batted straight up to the height of 20 feet? Right. First thing I like to do with these problems is I like to take and I like to draw my little picture. Kind of a big picture person. So it goes up and it's going to come back down. We know that up here at the very top we would have a velocity up at the very top of 0. V is going to equal 0. And as it comes back down, we know that whatever the velocity is here, it's going to be exactly the same, but in the opposite direction over on this side. So, what does this do? How do we treat this problem separate? Again, remember we have our equations. We're going to use the same equations we used with the other set of problems, but what's going to be special is how we take and treat the problems at the end. I took and rewrote the problem up here so we'd have a little bit more room to work. So, if we take and we bat this ball straight up to a height of 20 feet, that 20 feet is going to be my distance. So I know right off the bat I have a distance of 20 feet. Now one thing to remember is that we are in feet. Now, since we are in feet, that gives us a value for gravity of a 32 feet per second squared. And we're looking for some time. Right, we want to know how long he has to get into position. So these are the things we know. Now, previous problems we always took and we used VI as 0 because if we're dropping something off of, like in that one worksheet, when we drop the planter off of the window ledge, it takes and it gives you an initial velocity of 0. Well, this isn't the case because we know that as the ball goes up, comes to the top, and it comes back down, we're going to have initial velocity here. That initial velocity will be the same as the final velocity. But what we do know is we do know that right here at the very top, the velocity is 0. Okay, the velocity is 0. Now, how does that help us? Well, if we take and we consider just half of the path, if we split this symmetrical path right down the middle and just deal with half of it, we could use our initial velocity then as 0. So I'm going to take and I'm going to do that. I'm just going to consider the second half of the path here. Right? So from the top on down. And when I do that, when I make that consideration, that then gives me VI of 0. You have to remember, though, that that's only going to give you the second part here. Okay, the only second part. So let's figure out how long it takes us to go from the top down. All right, well, we've got time, so we can look at our equations and figure out which one we're going to use. I think it would be great here if we used, so I have my d equals VIT plus 1/2 GT squared. Again, because of this 0, that's going to take this whole factor here and it turns it into 0. So we're left with d equals 1/2 GT squared. So I'm going to take and solve for t. To do that, I'm going to divide by 1/2 of g and divide by 1/2 g. Oh, that would be a 2. Sorry, I don't know how to erase yet. And then t squared gives me 2d over g. So I'm going to take 2 times 20, divide it by gravity, which happens to be 32. And that 20 is in feet. My 32 is feet per second squared. So if I grab my calculator and do this calculation, I will come up with, okay. Now if you remember, that tells us that it takes 1.11 seconds to go from the very top of the path down. But the baseball catcher also has the time that it takes for the ball to go to the top. So in order to solve this problem, we aren't done yet. You need to take 2 times your time. And when you do that, 2 times 1.11 is going to give you 2.22 seconds. So the catcher has a little over 2 seconds, 2 1/4 seconds, or a little under 2 1/4 seconds to get into position and catch that fly ball. Right? So all of these problems, you use the same equations as we had before. We're using the same thing. The only difference is this last part right here where you take and you multiply the total time by 2, because then that will give you the path going up and coming back down. All right.